appreciate it. How's everyone doing? Good. It's the last day, I know. We've all pretty much walked both floors and we're all very tired, but we're almost there. And I really appreciate you guys taking a moment to sit down and to hear what I have to say. So thank you so much. Actually, I'm gonna take this off just to be a little more professional here. All right, here we go. So today I wanted to cover a little bit of the research that I've been involved in by utilizing consumer grade products to do high accuracy surveying. This is a highly contested subject, but if you've walked the hall, you've seen that these products continue to become more and more affordable, and they're using more consumer-based sensors to do many of the tasks that we used to spend hundreds of thousands of dollars on. So for anyone that doesn't know who I am, my name is Rami Tamimi. I am a professional surveyor, a PhD candidate at The Ohio State University studying geodetic engineering. I also make videos on YouTube about surveying and geospatial technology. We have one of the largest channels on YouTube, so we have a pretty strong foothold in the industry, showcasing new technology and workflows for surveyors. I've also founded the Survey School, an online education platform dedicated to educating the next generation of surveyors. And I used to actually be a software engineer over at General Motors. So this is actually a picture of me doing some sensor alignment and localization for our calibration boards. I want to briefly talk about a couple of things that you probably have seen before. I don't think we need to talk about them too much. One of those is UAV mapping. I think UAV mapping has been around now for about a decade, and we've seen it evolve. We've seen it go from just being these consumer level drones, sensors that you could pay $1,000 for, fly them, put some ground control on them, and then eventually be able to georeference the data to create a pretty standard, ortho image or point cloud that has some degree of accuracy. Now this process has been refined and it's improved. We now have RTK enabled antennas on our drones, so our trajectory data becomes more accurate. We're finding better bundle adjustment algorithms that improve the photogrammetry of our data sets. So this is a very robust method that we've actually, pretty much grown to understand now. So we don't really need to talk too much about this, but it's just something I want to mention, that you see the evolution of UAV mapping. Now the next one is smartphone mapping, right? This is also another, growing industry, something that has improved a lot, especially in the last 5 years. We all know that the iPhone has pretty powerful cameras. It has an IMU, it has a LiDAR sensor, and so theoretically you're able to use your iPhone to map different objects. And with the GPS information, you're able to then get some kind of trajectory data. The IMU helps you with that. The LiDAR sensor and camera sensor help you with that. But it really improves when you couple it with an RTK GNSS receiver. So that image here, you see this is with the Imlid Reach RX, and I'm using the Pix4D Catch app. I'm able to actually do survey grade mapping with centimeter level accuracy using just an iPhone. Not only that, we've now actually seen AR utility visualization applications where we're actually bringing in CAD drawings, things from the office, something that we can visualize into the real world. So now I'm bringing in my CAD drawings. I'm able to then visualize my location. And so this is a pretty good example. I'm looking at my utility plans. I've got a water valve. I've got a storm sewer. I'm able to see where the lines are, how they're connected based off of the utility maps that I got from my local municipality. So these AR applications continue to grow and they continue to evolve in the mobile and the smartphone mapping industry. And it's just a continuation of how consumer products bring us high accuracy data. So the main topic today is mobile mapping, right? I want to talk about my research and what I've done with mobile mapping and how we're able to use consumer products for this application. Now, when we think about mobile mapping, if we were looking at the cheapest, most affordable method of doing it, you're probably going to go to Google. You can go to Google Maps, you can look at the street view. It doesn't cost you anything. You don't even have to have a Google account to do this. Anybody can do this, it's absolutely free. And you may find a lot of information, whether you're looking for the way the roads are structured, looking at different features. If you're just looking for images, you can do this and anybody can access it around the world. On the more expensive end, on the very high-end enterprise side, you may get a Leica TRK Pegasus, costs you a couple $100,000 or euros. We're in Europe, but this is a very expensive sensor, and it provides you with very high accuracy data, but it also costs a lot of money. Like, is it really worth the trade-off? And so I start to think to myself, what if there was something in the middle? What if we had a consumer product that didn't cost hundreds of thousands of dollars that we can actually integrate for mobile mapping applications? And this is where I start to think about new smart cars like a Tesla. You see, Teslas have many dash cams that anybody can access. So this is a live view from a regular Tesla, and you've got, here you see 5, but there's actually 6 cameras on the new version of the Tesla that you can utilize. So these 6 cameras can actually give us a pretty good view of everything around us. And in my mind, I said, okay, so if I have these 6 cameras, what if we were to take the video feed from them and be able to generate a 3D model from our site? Now, the biggest drawback, unfortunately, is I do not have access to any of the GNSS information that is in the vehicle. So I've got to add my own GNSS in order to get that information. And that's where I can bring in an Imlid Reach RS3. So I just mounted this on top of my vehicle, and now anytime I drive anywhere, I can actually see where my geodetic position is. Now, in relation to the GNSS receiver, I need to know where all of my cameras are. So we keep the vehicle parked, and GNSS receivers have IMUs now, so we can actually tilt and figure out the position of all these cameras. And now I have a relative difference between all of the cameras and our GNSS receiver. So all that's left is to actually drive the vehicle and start collecting data. So this is a live view here, and the site that we're going to be taking a look at is just a driveway into a library, right? This is the library in our city. So I'm just driving down, I've got my cameras rolling, my GNSS receiver on the left is collecting data, and then you just see a live view of my vehicle as I'm driving around this little circle drive. And as I turn, you can see the live view of the GNSS is picking up exactly where I am. We're maintaining a fixed reading, so very nice. I'm able to keep all that information. Here is what the live view from the cameras looks like. Now, the beautiful thing is all these cameras are time synchronized, so we know exactly when they were recording. We see exactly when each frame was done, and it's all in the same time. So I just put all these videos together, and you can see when I hit play on all of them, they're all synchronized at the same time. Now, because these are video cameras, and because we really don't have any serious detail or information about these cameras, we have to figure out what the camera parameters are. And forgive me for anyone that hates math, we have to go over a little bit of math. I'll try to explain it as best as I can. But essentially, we're looking for the camera intrinsic and extrinsic values. This is your internal parameters and external parameters. So here's what I want you to visualize. I am a camera, all right? And inside of me, there is an image. And so what I need to figure out is what are the parameters between me, the camera, and the image inside me. The main 2 parameters are your focal length and your pixel size. By identifying these 2 parameters, we can actually see, okay, so between what the camera sees and what the image shows us, we're going to have some distortion. The wider the angle of the camera is, the more distortion we're going to have. So when we have a wider angle camera, you can get really close to an object. So now when you take a picture, right, even though the focal length is really small, if the sensor size is large, you're going to have what we call like the fisheye lens. That's when you see the borders of the image, right? In real life, that's not how it looks. So that's distortion. So we need to figure out what those distortion parameters are in order to correct them before we run any kind of photogrammetry. Now, the second set of parameters are the extrinsic parameters. These are the exterior parameters. So I am a camera, and I am taking a picture of this water in front of me. When I take the picture of the water, I need to figure out, 1, the distance between me and the object, and not just regular distance. I need to know the X, Y, and Z distance. These are the translation. So the translation is the X, Y, Z distance the camera is from the object. And I need to know, am I pivoted up, down, to the left, or to the right? This is the rotation. And what you see here are the camera translation and rotation parameters. So Having those two sets of parameters will give you not only the coordinates in the real world, but also the coordinates on the image. And you need to relate those two together in order to figure out your camera parameters. All right, we're done with the math. Let's go back to practicality. How do we actually find this information? Well, it's done using two methods. The first is camera calibration. Camera calibration is utilizing a fixed object that has a known distance. So what we typically use in the industry is a checkerboard. So what I'm going to do is I'm going to walk around my field of view, and I'm going to carry this checkerboard with me. This checkerboard has got known distances, so I know that the distance between one point on the checkerboard and the next is 85 millimeters. And as I walk around, the image is going to be distorted in different parts of the frame, and that's when I can figure out my parameters to fix the distortion. The next is the extrinsics. The extrinsics are points that we have known coordinates for. And the idea is you take your camera and you move around, or drive around in this case, and have the image continue to change the position of that one point. Now you need multiple points, right? So I've got some cones, I've measured the top of the cone and then the top of the stick. So now I've got 8 coordinates that I can use. So while I'm driving around, I can always reference at least 3 or 4 points in every frame. When you do this, and you run it through, specialized calibration software, you're going to be able to find the corners of your checkerboards, giving you the intrinsic values. And then here I am using my GNSS receiver to find the coordinates of my targets. All right? So this is the plan. We're going to find these values to help us determine what our camera parameters are. We've got a GNSS receiver that we're going to synchronize with the video, and that should help us be able to run photogrammetry for our images. So what software did I use to do this? Well, what I just explained is pretty scientific and research heavy. So the reality is there is no software that can do this. So we built our own. And we built an entire business around it called SurveyXR. And SurveyXR is designing software to help researchers and those that are trying to better understand how we do many of the things that all these softwares on this floor do, but teaching you how to do it yourself. And I want to show you a demo of what our software has done and what I'm doing to improve my research. So this is GeoFrame. All right, so the first thing we're going to do is create a camera profile. This will allow us to put all the parameters that we need for every individual camera on the vehicle. So we've got the front camera here, and we're going to specify the size of our checkerboard. So now I have a 9x6 checkerboard. I've specified that the distance between each point of the checkerboard is 85 millimeters. I want 1 frame per second for my sample video, and now I can download this image, print it out, and use it for the video that I will be recording. Now I can modify this. Maybe I want a 23x6. The software will automatically give me the right size board that I can download, so it eliminates any user error from that aspect. We'll switch this back to 9, and now we're going to upload one of our calibration videos. So this is a video I shot of the front camera. I am now walking around, and I'm being able to move my checkerboard around so that I can find all the distortion parameters. So I find, where do I start? Okay, where do I end? And that way the software doesn't have to sift through the entire video finding frames of me holding the checkerboard. All right, so I'm satisfied here. I can add more videos if I want, but this is one video, should be enough to give me some parameters. So it's going to go ahead and check for the corners of these checkerboard, or of the checkerboard. And there we go. We've identified all of the corners. We have an RMSE error as well as a reprojection error. So in the QA/QC step, I'm able to now verify that everything looks good. If I have any bad frames, I can remove them from the solution to ensure that I have the best intrinsic values. So I've gone through here. Everything looks to be fine. We meet the standards. Yeah, there's a pretty clear image right there with our identified corners. Very good. All right. Now we're going to start doing the localization. So the localization part, again, you need to survey your control points and you need to have coordinates for them. So we'll have to import these coordinates from our GNSS receiver. So I'm going to go in here, find my GNSS receiver, and then I can set my units. I'm American, so we'll be using feet. I'm sorry to all the Europeans, but we'll be using feet for our coordinates. And now I'm just going to georeference the position of all of these points. So the point here is the top of the stake. I'm going to select it. There we go. The next point is the top of the next stake. And the idea is I want to georeference as many points as possible that I can see in the frame. I think I only do 4 here just for the sake of time. But once I've identified everything in one frame, we're going to find a new frame. So we'll start going next. And there we go. We're moving the frame. So now the position has changed in the field of view so that we can actually calculate the difference, and that'll give us the extrinsic values for our camera. So I've done this for a couple of frames here. Looks like I'm still going. There we go. Now we've gotten all of our intrinsic and extrinsic values. We've gotten our parameters, our reprojection error, our RMSE error, our omega phi values, and we can also plot everything into a PDF report. So having a PDF report, we can now look at this information, save it for this specific camera. So this is for the front camera. Here are all the parameters that we need for our work. Okay, so now we've completed the camera calibration and localization for our first camera. The next thing we need to do is add that offset between the GNSS receiver on top of the vehicle and where the camera is located. So it's very easy. All you have to do is add the coordinates between both points, right? So I add the coordinates of my camera and then the GNSS receiver. I can do either the geodetic coordinates, which is the latitude, longitude, and ellipsoid height, or if I want to use UTM or state plane coordinates, I can use Cartesian coordinates and apply a scale factor to go from grid to ground. So here I am, I'm adding in my geodetic coordinates for both of those points. This is the list of points that we had from the collection that we did. And again, you can identify the units. I was in America, so we used feet. So this gives us all of our offset information. So now within XYZ, all of the images that we extract will have that offset applied to the position of the GPS. Now it's time to add in videos from where we actually were recording data. So driving down that driveway, I'm going to find where the starting point is because I don't want to extract any frames prior to when the vehicle was moving. So here we go, the vehicle is moving now. So we'll start here. Tesla likes to stop every 60 seconds, so it creates a new video file every 60 seconds. So we take the second video file. Again, once I stop moving, we'll stop it here. We'll say OK. And now I've got the start and finish of both of those videos. And there we go. We now have one camera profile completed with the parameters and the videos. Now I have 6 cameras, so we have to do this 5 more times. So I'm going to go through this process another 5 times with the left pillar, left repeater, right pillar, right repeater, and the back camera. Once I've completed all 6 camera profiles, the next thing to do is to add the GNSS information. These are all of the auto-collected points, and we just extract everything by exporting the data. And then I'm going to set my frames per second. So I'm going to set this to 5 frames per second, and now I'm going to begin the extraction. This will extract the frames from the videos and then synchronize everything based off of the time in which the video was recorded and the estimated time in which the frame was measured with when the GNSS receiver recorded a position in the same time. And we get a live view of each of these images being generated and where they're being placed in the location of the GNSS receiver. So I went through all 6 of the cameras, and once it's completed, we're going to now be able to download a zip file for all of the images just like that. Just for the sake of time, I'm going to move on to this one of my second to last slide. So this is GeoFrame. You can find it at SurveyXR.com. If you like the way I teach, you like the way I kind of present, I actually have an online school. And so this right here is the survey school. We have over 100 students globally, and we help educate the next generation of surveyors. We help provide knowledge and courses and opportunities in a community. We bring our students to conferences. So this is in the United States. We had 7 students come to this conference. Here at Geo Week, we actually have one of our students here too. He's going to present right after me. So you get to hear about what he's up to and his involvement in the school. So if this is something you think you're interested in, or you know someone that might be interested in, I highly encourage you to check out thesurveyschool.com. I'd love to connect with you guys. I'd love to learn more about what you guys are working on. So be sure to add me on LinkedIn. And if you're looking for some free resources, if you're looking to just start learning about surveying, you can always check out my YouTube channel. Thank you so much.